Hello students, welcome back. We just went through the exponential distribution. Now let's go to the next topic, gamma distribution. First, let's discuss gamma function. The gamma function is defined through this integral when alpha is greater than 0 and alpha is less than 0 or less than or equal to 0 to be a little more precise. We define it through this recursive equation. I hope you can clearly see that gamma of 0 is undefined. Why? When alpha is 0, we have 1/0 popping up. Is there anything else that you can see immediately? When alpha is greater than 0, we have this integral x to the alpha minus 1 power negative e to the negative x. They're all positive, so this integral here, so that's going to give you a positive value. Well, is there any more you can see? Let me show you the graph. The graph of gamma function looks like this. When alpha is greater than 0, then we have this integral, and that part gives you the right-hand side of this graph. It turns out, when alpha is pretty close to 0, then gamma of alpha blows up to infinity, and we have vertical asymptote. And as the alpha increases, come down, 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 we have local minimum and then increase back again. When alpha is negative, we define it through this recursion. Gamma of alpha is 1/alpha times gamma of alpha plus 1. And we do not have explicit expression, but that's okay, because what if alpha is between 0 and 1? 0 and negative 1, excuse me. Then alpha plus 1 is between 0 and 1. Therefore, gamma of alpha can be determined through this recursion because we know this quantity. It's coming from this integral. And then this is for alpha, so I have to replace alpha by alpha plus 1. So there you go. So when alpha is between negative 1 and 0, you can calculate gamma of alpha by this recursion, which gives rise to this integral computation, which is basically about this part. And we end up with this part of the graph. Why is it negative? That's because I'm multiplying by 1/alpha, which is negative. So what did you get? This part is now well defined. Previously, I had only the right-hand side part, which comes from the integral. Now, from this recursion, I got this part. So between negative 1 and 0, alpha plus 1 is between 0 and 1, and thus gamma of alpha plus 1 can be calculated through the integral. Now, what if alpha is between negative 2 and negative 1? Then alpha plus 1 is between negative 1 and 0. And then we can calculate gamma of alpha as 1/alpha times gamma of alpha plus 1, which we established already previously, this part. So this part we get from this part by multiplying 1/alpha. 1/alpha is negative, so this minus is flipped off to positive. You see here, we have this integral, which is gamma of alpha plus 1. That's always positive, but flipped over to negative because 1/alpha is negative. and 1 over alpha is negative again, so negative, negative, positive, we flip this flip. Let's do it one more time. Between negative 3 and negative 2, then alpha plus 1 is between negative 2 and negative 1, which we established earlier. So the same recursion formula gives you now this part, and then this part, and then this part, and then we can define recursively like that. So that's the gamma function. So do you understand why we have plus minus plus minus plus minus like that? That's because we are multiplying 1 over alpha, which is negative. Some further observations here. Let's see. 1 over alpha appears, so gamma of 0 is undefined. And consequently, gamma of negative 1 is also undefined. Let me see. Here are some further properties. You see, gamma of 0 is undefined. 1 over 0, so undefined. And then gamma of negative 1 is 1 over negative 1 times gamma of 0. But gamma of 0 is undefined, so that's undefined. Gamma of negative 2, 1 over negative 2, and gamma of negative 1, that's undefined, so it's undefined. And so on and so forth. Look at the graph again. We have vertical asymptotes, 0, negative 1, negative 2, negative 3, negative 4, negative 5, and so on and so forth. Okay, we went through a lot about alpha being negative. Now, what about alpha is positive? Let's study this integral. Well, in that case, we can do something like this. We can apply integration by part. Let's see. Here is the integration by part formula, going from 0 to infinity. Okay, that's the integration by part formula, isn't it? And how do you calculate this? Well, what is u in this case? X to the alpha minus 1. V prime is exponential. U prime is alpha minus 1 comes out, and the x to the alpha minus 2. And v is negative of exponential of negative x by taking antiderivative. So I can plug everything in here. So u is this, and then v is exponential. And let me put negative here. And u prime is alpha minus 1 times this. And v is exponential. And then how about this negative? It collides with this negative and becomes positive. Now, how about this part? Plug in infinity, we have e to the negative infinity, which dominates, so everything becomes 0. For detail, please check the L'Hopital's rule. Now, if you plug in 0, then 0 to the alpha minus 1 power, that's going to become 0 when alpha is greater than 0. When alpha is less than 1, that's a bit tricky issue. We're going to have to come back and discuss that. But when alpha is greater than 0, no problem. So in general, we have this 0. And then alpha minus 1. And then this integral. And what's this integral here? Compare that with this. You get gamma of alpha minus 1. So the conclusion is gamma of alpha is equal to alpha minus 1 times gamma of alpha minus 1. And of course, if I begin from alpha plus 1 instead of just alpha, then this is what I'm going to get. And this is going to be just alpha, and that's going to be just alpha. And therefore, gamma of alpha is equal to, flip it over, we have 1 over alpha times gamma of alpha plus 1. I don't need this red font. Let's go back. Let's go back to normal font. So this recursion holds for the first line as well. So you can regard the second line as an extension of the first line using this property. Furthermore, we can continue applying this integration by part or the same recursion to this one step further. See, this one here can be rewritten as like this. So use the same idea. Gamma of alpha minus 1 is alpha minus 2 times gamma of alpha minus 2. And then I can go to the next recursion. Let's see. I don't need this bold anymore. And then do the same thing to this guy here. Same recursion, same computation. This thing will be replaced by now alpha minus 3 times gamma of alpha minus 3. Excuse me. Okay, like this. And then continue. So we have alpha minus 1 times alpha minus 2, alpha minus 3, and so on. We're going to get a factorial. And go all the way down to, well, whatever the beginning was. Let me show you the conclusion. Same computation. In the end, when alpha is a positive integer, we get a factorial, n minus 1 factorial. It turns out that gamma of 1 is equal to 1. And actually, that's not too difficult to prove. You see, that's the definition of gamma function. And gamma is 1, so this is 1 minus 1. So we have 0 power. So this one drops out. And then the antiderivative computation of this is just... And this one goes from 0 to infinity. And plug in infinity. That's 0, and minus minus plus e to the 0 power. And that's 1, so we get 0 plus 1, that's 1. And this is 1. So in the end, what do you get? Gamma of n is n minus 1 factorial. Let's go back to the graph. We are looking at n minus 1 factorial. No wonder it's growing really, really quickly here. So gamma function is basically a factorial function extended over to all real numbers. One more thing. Oh, this is rather weird. Gamma of 1/2. If you plug in 1/2 and do your computation and do some integration by substitution, it turns out that we have e to the negative y squared, and this integrand is Gaussian normal. So gamma function has something to do with normal distribution. And do you recall the definition of the standard normal distribution had some square root of pi in the denominator showing up somewhere? It's related to this, by the way, this property here. And proof of this is rather complicated. It's coming from multivariable calculus with some change of variables to polar coordinates and things like those. For now, let's skip it. So we are talking about some function with rather important some interesting function with a lot of important connections to Gaussian normal you saw before, to factorials, and what kind of probability events are related to factorial computation. Hypergeometric is of course related to that, you see. An earned model without replacement, that's where we have all those factorial dropping down, you see. And then rearrangement. And there are a lot of things that are related to gamma function. So theoretically, it's very important. And as for the computational part, well, whenever you want any kind of gamma function, you can use computer algebra system. Gamma of, say, 0.67, ask Mathematica to calculate it. Okay, we went through gamma function. And then what about gamma distribution? Gamma distribution is a continuous probability distribution determined by gamma function like this. When x is greater than 0, we have this expression. This one looks very much like the integrand of the gamma function with appropriate change of variable, of course. And then we have gamma function down here directly. We have two parameters, alpha and beta. And when x is less than or equal to 0, nothing there. Now, is this a valid probability density function? That's a bit of a challenge, but we can actually prove it. We can calculate the integral from negative infinity to positive infinity of this density function. And if you do that, here's a constant, 1 over beta to the alpha over gamma of alpha. You can take it out. Wait a minute. This is redundant. Take it out. And what's left is this integrand, which looks very much like the integrand of the gamma function there. Looks like we need some change of variable. And what change of variable do I select? We take y as x over beta. So x is beta times y. So dx is equal to beta times dy. And then put that over here in this integral. Then x to the alpha minus 1 is beta y times alpha minus 1 power. And exponential becomes e to the negative y. And dx becomes beta times dy. And I'll do further simplification with this guy here. Then we have beta to the alpha power. You see alpha minus 1 power and another beta. And this whole thing is now gamma function, gamma of alpha. So we have the same thing as this denominator. So if you finish computation, yes, it is indeed 1. So yes, this is the valid probability density function. And that's what gamma distribution is all about. Okay, so much for gamma distribution, and we're going to meet again for chi-square distribution in a separate video.